Welcome to my talk on differential privacy and fairness in automated decision making. So I will try to explain these fairly philosophical topics, but in a mathematical way. So just a brief overview of me. So like I recently joined Ergo as a senior data scientist. Earlier, I was an independent research group leader at the University Hospital in Cologne, working on anomaly detection using self-supervised learning. And earlier, I completed my PhD in machine learning and computational biology from Max Planck in Cologne. Okay, so let's get to the meat of it. So I start with an example. So consider the risk scoring problem where, given a new applicant, the financial institution has to decide if they should get the loan. Increasingly, machine learning frameworks are being used to make these decisions, which are trained on a database of past clients. Assume that a past client now wants their data to be removed for future use. So this is available to them due to GDPR 2016. So the question is, would this removal lead to a significant change in the learned model parameters? So this is the main question that differential privacy asks. Now, coming to fairness, like automated decision-making also leads to decreasing human involvement, which raises concerns of bias and discrimination based on race, gender, sexual orientation, etc. Now, perceived lack of transparency leads to less satisfaction among clients. Now, the question is, can we provably ensure fairness among the protected classes as required by GDPR 2016? Now, from the financial institutions' point of view, they are concerned with achieving high accuracy, which directly translates into profits. Unfortunately, the three requirements of privacy, fairness, and accuracy cannot be satisfied at the same time, as we will see later. So the question is, how does one balance privacy and fairness in automated decision-making while maintaining this high accuracy? Let's talk about some biases that exist. So machine learning models in themselves can be assumed to be objective. So when well specified, they learn to make decisions purely based on data. So removes any subjectivity or bias which humans may have. However, even though the models may be objective, but the data is not. So for example, you have labeling bias. They imbibe inherent social ideological biases in historical data, which is usually against marginalized groups. You have the algorithmic bias, which is unbalanced sampling and noisy data from certain subgroups, nudges the algorithm to favor dominant subgroups with better sampling. Intervention bias. Past decisions, algorithmic or otherwise, lead to bias in newly generated data. And model interpretability. So GDPR 2016 requires the right to explanation for any decisions made. However, opaque black box models make it hard to detect and thereby correct biases using traditional approaches. Having said that, removing bias is not really that easy. So for example, removing sensitive variables from a data set might be an approach. However, this leads to redlining and reverse tokenism. So redlining is the effect when, for example, you're removing race data, but you can find other variables, for example, location or a postcode, which is a very good predictor of race, usually. The other problem is reverse tokenism, where, for example, a financial institution might reject a highly qualified candidate from a non-protected class and use it as a reason to reject candidates from the protected class, but with lesser qualifications. Again, incomplete data can be recovered with high probability, for example, using matrix completion algorithms. This phenomena is known as birds of a feather flock together. So it is not enough that if I personally want privacy and I just not answer a couple of questions, that is not necessarily remaining private, because you can actually guess what the correct answer would have been. Demographic parity is also not enough. For example, gerrymandering in US elections. By law, every person has the same ability to vote. However, not every group of people have the same effect on the outcome of the election. In all of this, it is important to note that there is no ground truth. Hence, it is empirically impossible to be unbiased without making explicit assumptions. So let's try to define what these notions of privacy and fairness are, like technically. So differential privacy. So clearly a person's privacy cannot be compromised by a statistical model based on a data set if their data was never in it. Consequently, the goal in differential privacy is to ensure that each individual in the data set roughly has the same privacy, as if their data was removed. So the idea is that whether a single person's data is in the training set or not, like you should get more or less the same result. So this is like made exact via this definition, which just says that if M is your randomized algorithm learned on two data sets X or X dash, which only differ in one point, then for all possible outputs, it should satisfy this inequality. So which is just that the probability that it is correct based on the algorithm based on X is e to the power epsilon into probability that it is correct based on X dash, and there's a delta noise error term there. And so any algorithm that satisfies this inequality is known as epsilon delta differentially private. Now this definition seems a little cryptic. However, in practice, it can be implemented rather easily. So the main point is that we want to limit the statistical influence of each individual data point on the learning algorithm. So that means that if we modify the empirical risk minimization problem by adding this epsilon term, then we can define the influence of upweighting any arbitrary data point via this influence, this type of an influence, which is based on the Hessian of the data of the model at the learned parameters, and then the gradient of with respect to the parameter evaluated at the data point. So this would be the influence of this data point on the parameters. So a differentially private learning algorithm would simply limit the influence of each of the data points on the empirical risk minimization problem. So we want this to have a clipped at a maximum value. So that's essentially what how you would implement a differentially private algorithm. So let's look at some notions of fairness. So now fairness is less easy to define, and there are quite a few different ways of looking at fairness. So for example, you have well-calibrated predictions, so like where predictions on random subgroups match the predictions over the whole population. For example, this is common in medical testing and diagnosis. The question is decision-making applied uniformly across different groups of patients? The second way to look at it would be balance for the positive class. So that is, the false positive rate is under control. So the average score received by people constituting positive instances should be the same in each subgroup. For example, if you have a advertisement or a commercial content on social media, like the certain ads might be shown based on gender or racial groups. For example, females may be shown lower paying job adverts compared to equally qualified males. So this would be considered unfair. Another notion of fairness would be balance for the negative class, so false negative rate. So average score received by people constituting negative instances should be the same in each subgroup. This is true in the criminal justice system. So decisions about bail, sentencing, parole are increasingly made based on models which predict probability of recidivism. So for example, this compass risk tool is very common in the US justice system. And the question is that, do you really want to make a decision on keeping someone in jail where the algorithm acts differently when it comes to the making decisions based on who stays in jail? You do not care about who goes away, like who's let out, but more important is who's going to stay in jail. Another notion of fairness would be individual fairness. Here, models are Lipschitz continuous with respect to a certain notion of individual similarity. So Lipschitz continuity just means that it doesn't have to be like continuous with like, as you know, in the standard definition, but just that the jumps between 2 points should not be too high. So one example is in credit scoring. So are two similar people scored similarly? So if you change the attributes a little, their scores should not change too much. However, for example, in FICO scores, you can do strategic manipulation and change the FICO scores quite a lot. So this might be considered unfair. Now, with fairness, there are some impossibility results. So you cannot really achieve fairness to the highest degree in every situation. So notions of group fairness intuitively ask that our group model should have the same effectiveness regardless of group membership. One might therefore hope that it would be feasible to achieve all of them simultaneously, i.e. achieve statistical parity. So like whether it's race or sex, like independent of whatever you are choosing, like the prediction algorithm behaves the same way. However, it was shown that it is impossible to do so, even approximately. So in Kleinberg et al. In 2017, they showed that unless the classification algorithm that you're using is perfect and all underlying subgroups are statistically equivalent, it is impossible to achieve statistical parity. So clearly in the real world, like you cannot achieve a statistical parity. So there is always going to be a trade-off between how much fairness you can achieve based on these 4 different types of measures of fairness. Another problem is that of composition. So most decision-making processes, automated or otherwise, are based on multiple decisions being composed together. So, for example, in mixture of experts model or sequential filtering. However, unfortunately, compositions of individually fair decisions may not be fair. So even if you make sure each and every component is fair, that does not mean the whole thing is fair. So for example, this ranked choice voting system with more than 2 candidates can be unfair. So this is the very famous Arrow's impossibility theorem. This is from the 60s, and the guy Arrow even won the Nobel Prize for this. Okay, so, and therefore it is important to look at the problem of fairness holistically while training the model. Now, the interaction between privacy and fairness. So since privacy is achieved by limiting the influence of the whole data point, there is a trade-off with controlling fairness, which requires more fine-grained analysis. So essentially in privacy, what you're doing is you're adding some noise to your data point so that you are making it less identifiable. But in fairness, you want each data point to be extremely well identifiable so that you make sure that it's not being like the predictions based on it are satisfying these fairness criteria. It further implies that unlike privacy, ensuring fairness does not imply increasing generalizability of the model. Now, when you're doing privacy, because you are making your data set independent of changing a single data point, you're actually making the model more generalizable. Because it's a natural thing. So because you're trying to make your model as independent as possible from variations in your data set. But the question of privacy is, the question of privacy is very different. So there you need to know each and every, like what the values of the different people are. Therefore, the models of interest in practice ought to be both differentially private and fair. So now, how do you actually learn these differentially private and fair models? So like when you're, like any learning problem can be reduced to the problem of empirical risk minimization. So you have a loss function, you have some F, which is your model, and Xi and Yi are your data sets. So Xi is your training data and Y is your predicted label or regression model, like whatever you are trying to do. So you have two pairs of Xi, Yi. F is the model, which belongs to the H model space. L is the loss function, could be cross entropy, could be least squares, whatever that you're choosing. And then you solve this optimization problem to learn your model. In fair risk minimization, essentially, you are adding this fairness constraint to the learned model. So in practice, this is rather straightforward. So like whenever you are doing some kind of a classification problem, you just need to add this extra term, which takes into consideration the type of fairness that you need, and which is obviously problem dependent. So based on what we discussed before. Now, when it comes to differential privacy, so like in this work, we used this differentially private stochastic gradient descent. So the algorithm is actually rather simple. So you compute per sample gradients. So for each data point, you calculate the gradient. You clip these gradients so that the influence is limited, is bounded above. Because if you remember, the influence of each data point is based on the Hessian multiplied by the gradient. So if you just limit this gradient, you can limit the whole influence. And then you can pretty much follow the standard, like you can aggregate these gradients back into the, for the single parameter gradient. And in the end, you add a delta noise to each of these learned parameters, and then go through the standard stochastic gradient descent iteration. So in practice, it's just a couple of lines of code that you have to modify to the standard SGD. So the rest of the talk, I just wanted to go through one data set and see how you can actually apply this. Yeah. Colab Notebook, which the viewers can try it out if they want to. So this is the differentially private and fair credit classification. So in this notebook, I basically talk about this data sets. It's like UCI data set, which consists of 30,000 clients and their credit transactions in Taiwan. And these are the bills between April and September 2005. And the task is to predict if the client will default on the card payment in October 2005. So this is just getting the data set and like just seeing what the data set looks like using the UMAP algorithm in 3 dimensions. So looks, I have to say, looks rather structured, but we want to see how well things like sex, education, marriage, age, etc. actually affect the ability to repay. So that's essentially what we want to try. So here I have already run this code, so that we don't have to wait, but you guys can try it out. So essentially what I did is I introduced a variable called limit balance, which made it especially predictive for the female group. So this is a synthetic feature made so that we make sure that the data is like unfair to females. Like if you train standard algorithms, they would be unfair to females, because I was not sure if it would work otherwise. Okay, so like after making this, adding this synthetic data set, so this is what the data set looks like in 3 dimensions. Okay, so now the next step would be to actually run a logistic regression with this notion of differential privacy. So the idea is that if you just, this is the standard scikit-learn logistic regression. And if you run this, train this model, it gives you 77.9% accuracy based on this non-private way of learning logistic regression. However, if you now train it using this package called, so I use this package called diffprivlib. So this is from IBM. So they have a package for doing these types of logistic regressions and linear regressions. And if you learn based on that, which is just doing this gradient clipping, then you basically get more or less the same type of result, but now your data set, now your learned model is differentially private. So what does that mean? We want to know the trade-off between privacy and accuracy. So in this plot, what you see is these, as I'm increasing this epsilon, so in my epsilon delta accuracy, so I kept my delta constant to 10 to the power minus 5, and epsilon is changing, and based on that, I can see my the accuracy keeps increasing. So there was some problem with convergence in this region, and that is because the logistic regression model itself was not converging when you reach this level of epsilon. So the point was to then choose a different model, and see if this improves. So what we next, what I do is train a light GBM classifier. So this is the state-of-the-art gradient boosting machine classifier, which is winning all the competitions at this point. So I use that to train the exact same model. And here you can see that the synthetic feature that I created has the maximum importance, while all of these different payment times and payment amounts have lesser importance. And the question is, how can we see if our model is fair towards males versus females? So I created this metric for false positive rate and the false negative rate. So this is what I spoke about, 2 of the metrics for measuring fairness. So here you can see in the false positive rate case, between males and females, this is quite comparable. However, in terms of false negative rate, they are quite different. So it's much more likely to reject a female candidate than a male candidate. But males are accepted much more often. Okay. So now we get some more metrics. So we calculate all the different metrics that we spoke about. So for example, you have the overall selection rate is 26%. So 26% of all applicants are selected to get the loan. You have a demographic parity difference of only 5%, and a demographic parity ratio of 82%. That means for every 1 male, you have 0.82 females. Now, this means that the overall balanced error rate is 0.22, while the error rate difference is 0.17. So that means there's a rather huge difference between the balanced error rate between males and females. The false positive rate difference is less so, but the false negative rate difference is quite a lot. Even the equalized odds difference is quite a lot. And the overall AUC, which is what like the company would be interested in, this is also quite different for males and females. So now we want to mitigate this type of false negative rate difference using some post-processing. So this is when we are training the data using differentially private and controlling for these fairness criteria. So false negative rate difference. So if you run the code, okay. So if you run the code, then you get like your overall selection rate decreases to only 8% from 26% in the beginning. However, now the demographic parity difference has reduced even more. And we have achieved demographic parity ratio of 0.92. So it is a big improvement from 0.82 to 0.92. Now, the error rate has now increased, so from 0.22 to 0.4. However, the difference between males and females is almost non-existent now. Same is true for the false positive rate, false negative rate, and the equalized odds difference. However, now you can see the problem is that the overall AUC has dropped from 0.85 to 0.59. So from the point of view of the bank, now you are much less accurate in your predictions, even though you have achieved fairness between the two sexes. So the point is that now we need to somehow figure out to increase this AUC by making a trade-off between increasing these a little bit. So we do a grid search, which optimizes for the AUC, but so that this does not increase too much. And that would be, so I do. Okay. So this is after doing the grid search. We see that like the overall selection rate has again increased to 0.26, but we have a parity difference of only 2%. We have maintained our parity ratio. We have again reduced our error rate to 0.26, but we have still maintained our, or like increased only a little bit, or 6.5% error rate difference between the two sexes. These are also all very small. So like the false positive rate, false negative rate, and equalized odd difference. But the main point is that we have increased our AUC quite a bit. So it's still lower than 0.85. You cannot avoid that, but it's still much more respectable compared to 0.6 that we had before. So essentially, that's the main point here, that you cannot avoid making these types of trade-offs. So in summary, ensuring fairness is hard, even if measuring is relatively easy. Complete fairness is impossible among all groups. There are always trade-offs. Ensuring fairness is expensive. So like it's computationally expensive and is also in terms of reduction in your AUC. So like it is expensive in terms of reduction in profits. And ensuring differential privacy is relatively easy, and it also improves generalization performance of the learned model. Thank you for your attention.